Conjugacy. In the context of Bayesian inference, a conjugate prior for a parameter or a set of parameters theta for a model is a family of probability distributions over those parameters, p of theta, such that when I condition on data d, the posterior over theta, p of theta given d, remains within the model family. The power of conjugacy is that it allows for efficient and exact computation, because with the conjugate prior, I can analytically express in an exact closed form the posterior distribution, that is the effect of data on my update about my beliefs theta. In the general case, it is not necessarily possible to analytically express the posterior, even if the pieces going in are all closed form. And so the fact that you can do this with conjugacy is very powerful and effective because it keeps your inferences fast and exact. So I'll walk through a simple example in the context of the binomial distribution, which should be very familiar to you at this point. The canonical example here is the toss of a weighted coin. The binomial likelihood for success parameter coin weighting p is that if I flip the coin n times, the probability that r of them will be successes or come up heads is n choose r times p to the r times 1 minus p to the n minus r. Now the beta distribution is conjugate to this. This is the form of the beta distribution. It is a distribution over success parameters for the binomial distribution. So it ranges continuously from 0 to 1. And the beta distribution has two parameters, alpha 1 and alpha 2, which effectively function sort of like pseudo counts. There is something along the lines as if you had gotten up to an additive constant, alpha 1 successes and alpha 2 failures in alpha 1 plus alpha 2 coin flips before seeing any data. And the beta distribution is, its probability density is proportional to p to the alpha 1 minus 1 times 1 minus p to the alpha 2 minus 1. And it is defined for alpha 1 and alpha 2 greater than 0. And in the bottom left, you see different beta distributions. So for example, if I set alpha 1 and alpha 2 equal to 1, we get a uniform distribution. If I set them to be the same and greater than 1, then I get a distribution which is peaked around 1/2 and then tails off farther away from 1/2. If I set them not to be the same value, then I'll get a distribution which is has a mean that is not at 1/2. And if I set them both to less than 1, I get what is called a sparse distribution. That is a distribution that puts very little probability mass in intermediate ranges of p, but relatively more probability mass in extreme values of p. So values of p that are either very close to 1 or very close to 0. Now, let's suppose that I observe data d, and I'll summarize this as I effectively n coin flipped with r heads. And Bayesian inference tells me that I can rewrite this as the likelihood, it's proportional to the likelihood times the prior. So the likelihood is the probability of d given p and the two alpha parameters. The prior is p of is probability of p given the alpha parameters. So notice that the binomial distribution is giving us the likelihood, the beta distribution is giving us the prior. Since the binomial likelihood doesn't depend on the alpha parameters, I can actually just get rid of these. Just cross these off for present purposes. And I can directly use the binomial likelihood function. And so I rewrite this, the first part of it. So this part becomes this. This is just copying over the binomial likelihood. And then the prior comes from the beta distribution. So I just copied over the beta prior. Now, you'll notice here that the beta and the binomial distribution have a commonness of form. That is that they both have a p to the something times 1 minus p to the something component in them. And I'm going to use this. This is the crucial source of conjugacy. I'm going to use this to actually just rewrite this expression by grouping terms. So first of all, I'll take these two p to the something terms and I'll group them together. And then I'll take these two 1 minus p terms, 1 minus p to the something terms, and group them together. And when I do that, I get p to the alpha 1 minus 1 plus r, and 1 minus p to the alpha 2 minus 1 plus n minus r. And one more thing I can do is that notice that since I'm actually only dealing with up to proportionality, and I'm putting a probability distribution over the success parameter p, and p does not affect n choose r. The value of n choose r is constant with respect to p. So without affecting proportionality, I can just drop the n choose r term. Just going to get rid of that. And so I'm left with this form. The posterior is proportional to p to the alpha 1 plus r minus 1 times 1 minus p to the alpha 2 plus n minus r minus 1. And now notice that these two things, these are both positive because alpha 1, alpha 2, n, and r are all positive, and r is less than or equal to n. And so what that means is that actually this bottom equation is another instance of a beta distribution. It has the same form. And that's what we mean by conjugacy. We have updated with data D, and our posterior on the success parameter P has stayed within the same model class as the prior. That is what conjugacy is. So to show you an example of this in a specific case with a specific set of observations, a specific choice of the prior, I'm going to choose alpha 1 and alpha 2 equal to 3 to express sort of a mild belief that the coin is somewhere in the neighborhood of fair, as illustrated on the bottom left. And now suppose I flip the coin 10 times, and this is what I get. A sufficient statistic from this data set is to summarize it as I flipped the coin 10 times and I had 7 heads. So the posterior now, I have it in this form, and I'll explicitly write this alpha 1 plus r as alpha 1 prime, and alpha 2 plus n minus r as alpha 2 prime. And so now I can just say the posterior is actually a beta with parameters alpha 1 prime and alpha 2 prime. And alpha 1 prime is alpha 1 plus r, so that's going to be 10. And alpha 2 prime is alpha 2 plus n minus r, and that's going to be 6. So now I have a new beta with parameters 10, 6. And that looks like this, the blue in the lower right. So I've updated my prior by incorporating data, and I've stayed within the beta family, and I didn't have to do any explicit calculation. So I didn't have to, for example, go to every particular value of the possible values of P and multiply through the prior by the likelihood, and then take the resulting set and renormalize. That would be a very onerous and taxing thing to do because, well, there's an infinite set of possible values of P. In fact, it's uncountable. So I would actually have to do something approximate if I were going to do something numeric. But the power of conjugacy is it allows me to do this exactly. So I actually have an exact answer that covers the entire uncountable infinite space of possible P. This also is applicable to other kinds of distributions, including in the continuous space. So for example, for Gaussian distributions, let's imagine in a context of unsupervised learning, or supervised learning even, that I have these observations that I believe are coming from some underlying category, and they're in a multidimensional space, and I believe they're Gaussian, and I want to infer likely Gaussian parameters, mean mu and covariance matrix sigma, from these data D. So how do I do that? Well, you're familiar with the Gaussian likelihood function. I'm not going to review that here. What I want to just tell you is basically a simple example of how this is done. So in practice, an effective conjugate prior when you don't know either the mean or the covariance matrix is as follows. You actually start by saying, I'm going to condition the mean on the covariance matrix. And my prior, given any covariance matrix, for the mean is going to be a normal distribution centered around some mean mu naught. And the covariance matrix will be that covariance matrix sigma. My prior on the covariance matrix is going to be what's called the inverse Wishart distribution. And this takes two types of parameters. So one is a positive semi-definite scale matrix, which you can think of as sort of the average covariance matrix in some sense of average. And it's covariance matrices have an interesting structure in a multi-dimensional space. And so it's a little hard to say what a single point is as average, but you'll see an example of what that means. And then the second parameter is nu, which is the degrees of freedom, and that functions a little bit like pseudo observations, just as the alpha parameters in the beta distribution function sort of like pseudo observations. So when nu is large, the draws from the inverse Wishart distribution are all going to look a lot like S. When nu is small, the draws are going to look more variable. So as an example, let's suppose, so in the gray circle here that I have on the bottom right here is going to be S. That's just actually the unit circle in this case. So it's the covariance matrix is 1, 0, 0, 1. And I have drawn samples, just the horizontal lines of ellipses are samples from the inverse Wishart distribution with the minimum nu equal to 2. So nu has to be equal to or greater than the rank of sigma. And then nu equal to 5, which is a higher value. And what you can see is that, first of all, there's variability in both the size and the shape of these ellipses, as different draws, so there's some uncertainty about that. But furthermore, you also see that there's more variability when you have low values of nu and then when you have higher values of nu. But the other thing but because of that, you should also see that the actual choice of S and nu is going to influence the prior that you put on categories. And so this is a way of building in information about what categories are likely to look like in a continuous space. So once we've done that, we can then use the conjugate methods to compute exact closed form expression given Gaussian distributed data, which will be joint inverse Wishart normal distribution over the mean and covariance matrix. So, for example, this might be a very high probability posterior characteristic ellipse for a Gaussian, and these are lower posterior density ellipses. But there's a continuous distribution over the infinite set of multivariate Gaussians given this data that is guided by the data and the prior. So that's conjugacy.